So today we discuss last chapter of part 1, that is electromagnetic waves. Last chapter is electromagnetic waves. That's a very important chapter. Okay. Here actually today's class we discuss that Maxwell's law. Okay. Or that Maxwell's equations. Here the Maxwell actually modified the Ampere's concept. Okay. And we know that current passing through the wire produces a magnetic field, or vice versa. Also magnetic field produces a current, that's an induced current. But Maxwell noticed that there is some inconsistency of the Ampere's law. Notice that there is some inconsistency, some mismatch here. And he suggests that there is some additional current, and this additional current is called that a displacement current. And this displacement current concept is built by Maxwell's. Now that final Ampere's law is perfect. So before that there is some mismatch. Okay. So in Maxwell's equation, James Clerk Maxwell's the Maxwell's equation, actually this Maxwell equation is very important in students communication. Okay. Radio communication, telephony system, waves, electromagnetic waves, or electromagnetic theory. The Maxwell equation is the base building block of electromagnetic theory. So you can't ignore that Maxwell's equation, because today's life, the internet, the first generation, fifth generation, all are depending on wireless communication, all are dependent on electromagnetic waves, and these are belongs to the Maxwell's equations. Okay. So here Maxwell first modified a Ampere's law. Ampere's law. Okay, because there is some inconsistency in Ampere's law. Okay, and this inconsistency recovered by Maxwell. So where is the inconsistency? Where inconsistency came from? Suppose we choose a capacitor connected to a variable source. The source, now we say the variable. So we see that if there is a variable source, so there is a positive charge here and negative charge here. Okay, and the current passing through that wire, that is a I is a function of t, and this current is called conduction current. It's called conduction current, and this conduction can also produce a magnetic field. Okay, suppose we choose magnetic field at that point. Suppose the point P, calculate the magnetic field. So current passing through the wire, this line. So we choose a, suppose some Amperian loop. There's a fun, and the current passing to the center point. For we choose because the center point, because for easy calculation. Okay. So suppose radius be the r, this radius r. So now apply the Ampere's law, that is integral b dot dl, that is mu 0 I t as a conduction current. So we get b integration dl, we get l, and we get that is a dl means a l, that is a 2 pi r mu 0 I function of t. So you get magnetic field at point P, that is equal to mu 0 I t by 2 pi r. That's the easiest way to calculate magnetic field at any point, because with the help of Ampere's law. But there is a mismatch. Okay, when we choose some arbitrary shape like that, arbitrary path is look like this. Suppose we choose this path, now look like a pot shaped path. Okay, these are the pot shaped path. This side is the open, this side is the closed. And this surface, you see that the current where is end here. If there is a wire end, so no current passing through that portion from Ampere's law. If there is no current at that portion, so means there is a magnetic field at point P equal to 0. Okay, so magnetic field at point P 0. So here we choose a pot surface, pot. So magnetic point is 0. So there is a mismatch here. Actually, the Ampere's law states that this point is a calculated magnifier at this point is do not depend on any arbitrary surface or arbitrary loop, independent of the surface. But here you see that when you change the surface, so obviously the magnetic field is changed. Okay, so there is some inconsistency. So inconsistency is that the magnetic field is independent. Is independent on path or surface or surface. But you see that there is an Amperian loop. But here, when you choose a pot-like surface, so there is a magnetic field B point P with a 0. You see that there is a dependent here. Okay, so there is some inconsistency. There is some mismatch here because there is a dependent. It is not independent. Okay, there is some dependent. But that inconsistency recovered by Maxwell's. Maxwell's proposed that suppose there is some electric field obviously in that direction, and this electric field only depend on charge, amount of charge. If the source is variable here, so more charge are stored in here, these two plates, more charge. If there is a more charge, the concept is like that. So there is a electric field, there is a more charge, charge also change, the Q also change. Okay, keep in mind if the source is variable, source is changed, so Q also change. So here that's the electric field. So now we choose any arbitrary path at point here, we choose a path here inside between these two plates. So we see that this phi electric field crossing this surface, this spot-like shape, or say choose any arbitrary path here. Okay, yeah. So that is equal to electric field E some area A. Okay, and now this change in flux, how to change, because the source is changed here. If source is increased, so charge store here also increase. So now d phi E dt also increase. So now suppose that is actually the integral of E dot dA here. Okay, now that is d dt of E dot dA, and that is equal to, from Gauss's law, Q over epsilon naught. From Gauss's law and electric field, from Gauss's law in electrostats. Okay, now that is equal to get Q over epsilon naught, and sorry, the differentiate of d dt of Q over epsilon naught, and epsilon naught is the permittivity of free space. So outside the differentiation, so 1 by epsilon naught, that is a dq dt. Okay, that is equal to, you get a d phi E by dt. Now epsilon naught d phi E dt, that is equal to dq dt. Rate of change of charge, that is equal to some current, that's I. And this current Maxwell named, that's the displacement current. This current is called displacement current. Important concept, the displacement current. And final expression, that is displacement current id, that is equal to epsilon naught d phi E dt. Okay, and that's also, that is equal to d dt times epsilon naught, that is integral of E dot dA. Okay, okay, that's the displacement current proposed by the Maxwells. Now the Ampere's law should be modified. Okay. So here the another question came, that is why this current, this is called a current. Okay. Why this called any other name? Suppose why this called current, or it is called a potential or some other name. Why this called current? Why is called current? Because a change in electric field also produces a magnetic field. Here the answer is change in electric field also produce magnetic field. Similar like when a moving charge, okay, also produce a magnetic field. Moving charge means a conduction current also produce a magnetic field, same as this. Okay, so here when you choose, suppose draw a new diagram here in capacitor. The capacitor, choose a capacitor I function of t, and we choose a point P here. Okay, so point P, and here is a producing magnetic field at point P when you choose here, or also when you choose inside that point, here also produce a magnetic field with the help of Ampere's law. Get that? And when you place that, is look like this, and suppose a positive charge here, there is a positive charge, so we get magnetic field in that direction. Okay, magnetic field in that direction B. Okay, so rate of change of magnetic field, rate of change of electric field, the change in electric field also produces a magnetic field. So change in electric field means suppose here d dt of electric field, suppose you say that that is a E, and when you say the electric field, so there is a epsilon naught. Okay, and if there is a epsilon naught, suppose multiplied by some area A, that's we get a current, displacement current. Okay, so change, okay, in electric field also produce a magnetic field. So epsilon naught E, suppose epsilon naught means that is epsilon outside, and A is the area, so d E A by dt, and EM is phi, so d phi electric field by dt. That's the same expression here. These also produce a magnetic field. That's why this current is name is displacement current. Okay, clear why this current is called displacement? Why this ID is called displacement current? Okay. Now the Maxwell's law is here modified. So here the final expression of Ampere's law. What is the final expression of Ampere's law? So Ampere's law says that is a B dot dl, that is equal to mu 0 total current. And now the total current have two parts. Mu 0, one is a conduction current, or I is a function of t. So that's the conduction current. Okay, that's the conduction current, and other is the displacement current ID, and that is a mu 0 IC, and here is a mu 0 ID. So displacement current, that is equal to epsilon naught d phi E dt, that is B dot dl. That's the modified Ampere's law, or you can say that is Ampere's Maxwell's law. These are called Ampere's Maxwell's law. Okay, so here are the four equations of Maxwell's. When starting discussion, there is a equation, Maxwell's equation. There are the four Maxwell equations, and here the four Maxwell equation is the very important, very important in electromagnetic theory. That is the Maxwell's equations. The first equation is Gauss's law in electricity or electrostat, we get E dot dA, that is equal to charge enclosed by epsilon naught. Next, Gauss's law in magnetic field or magnetism, that is equal to B dot dA, that is equal to 0. That is not equal to 0, that is equal to 0, because magnet have dipole, not monopole. But electric field depend on a single charge. Single charge also produces electric field, but a single monopole of magnet is impossible. Okay, that's why the magnetic field closed loop here get a 0. Third is Faraday's law. Okay, so what is the Faraday's law? That is equal to, you get integral E dot dl, that is equal to minus d phi b dt. So here is derivation of Faraday's law. It's very easy. Okay, so we know that suppose a work done, a moving charge from one plate to another plate, charge from one plate to another plate. So there is impossible here, but we consider the moving charge one plate to another plate. Suppose that is equal to force into displacement. Suppose there is some S, say that all L. Suppose there is a length, so that is a L for better understanding. So and put a S, so maximum number of students think that there is a considered surface. So that's why I put a L here. Okay, force into displacement, and that is force that is equal to Q times E. That's obviously texture here. That dot dl, and now W by Q, that is equal to integral E dot dl. Suppose E dot dl means here we choose a charge move in closed path. Move in a closed path. Move in a closed path. So here this E dot dl, so better understanding for diagram. Suppose there is an electric field in that direction. Suppose there is an electric field. We choose a conductor, and inside choose any arbitrary shape here. Suppose these be that, suppose is a small r, and that magnetic field in that direction. Okay, B, suppose magnetic field in that direction, here magnetic field in that direction, here magnetic field in that direction. So there is some rotation here. So actually the charge rotation, magnetic field here. So electric field on the cross product. Suppose there is a path here. Okay, so W by Q. Okay, the W by Q, we get that's a potential, that is E dot dl. Okay, and there is a potential means from Faraday's law, that is equal to minus n d phi b dt. And now consider n is a number of turns with a 1, so you get b equal to minus d phi b dt, and that is equal to integral E dot dl. This is path. Okay, there is some path of closed integral here. Okay, that's the Faraday's law. And number fifth or final derive here, that's a Ampere's Maxwell law, that is equal to B dot dl. We get mu 0 conduction current, mu 0 epsilon 0 d phi e dt, and these expressions are ID, displacement current. That's the modified Maxwell's equation. Okay, that's clear the concept. What is the modified Maxwell's equation and why that modify is needed? Okay, what is the displacement current, and that's actually discussed here, not here discuss what is electromagnetic theory. So next class we discuss what is electromagnetic theory. Okay, here I basically discuss only a displacement current and Maxwell's equation. Okay, so if you have any doubt, please ask in comment section or mail me. I will try to give the answer. Okay, so today in the class here. Thank you.